All right, so Gregory will be our next speaker. He'll be talking about some work on specifying and verifying a microhypervisor.
All right. This is work that we worked on while I was at BlueRock Security with Hoang-Hai, and I will be giving the talk. So the context, if you've talked with me over the last 7 years or so, you've probably heard about this crazy project we have. The big ambitious goal is to verify a hypervisor stack. And that's a product that BlueRock Security has been working on, and I've been working on the verification of it for a while. So this hypervisor stack is a microkernel hypervisor-based system. It works on the Nova microkernel. And user space applications in a microkernel stack, or microkernel architecture, provide the interesting functionality that you would actually think about. So you can think about the microkernel hypervisor, Nova here, is kind of like a hardware abstraction layer. Provides very low-level pieces, similar in the academic community to something like SEL4. So the focus of this talk is about the verification of just this one component. Other work we've done is focused on the verification of these other blue components. We've got some interesting work out about verification of virtual machine monitors and things like that, but in this talk, I'm just going to focus on Nova. So what's a microkernel hypervisor? Microkernels have this philosophy that everything that is not absolutely necessary to be in the trusted computing base can be removed from the kernel. And so what this does is we look at, or I should say, when I say we look at it, the developer of the microkernel hypervisor, Nova, has divided the system resources, which are down here, things like memory, interrupt controllers, and things like that, and exposed them via several APIs. You've got an API to the CPU that provides things like threads. You've got APIs to memory that allow you to control page tables, APIs to interrupts and devices. Okay, and we've done work that gives us a specification for verifying Nova, which is written in C++, and doing verification of those applications on top of it, which are also written in C++. And the nice thing about our approach, so we use separation logic everywhere, is that you basically get the same sort of nice reasoning principles that you would think about, and they're very naturally captured within separation logic. And I'll make a note here, everybody goes, tries as hard as they can to get rid of concurrency. When you do a system like this, concurrency is unavoidable. And it's even worse than you might think, because normally we think about, well, I'm racing with myself, with my own things, so I can maybe put a lock here or something like that. Microkernels and things like this, they race with other hardware, right? So half of what's interacting with page tables is the code that you wrote, and the other half is the MMU, which some Intel engineer or ARM engineer designed. So you don't get a choice on what they do. All right, so at the technical level verification, we're doing everything in separation logic. So we're starting with an axiomatic semantics of C++. That's this brick program logic that we developed at BlueRock. And then we do separation logic proofs of the actual C++ code that runs, and the specification of Nova is reflected in C++, in separation logic. And we're using Skylabs separation logic automation to do those proofs automatically as much as we can. On a logistical side, this is a big project. There's 15,000 lines of code or so, very highly concurrent and very subtle, and built with a very keen focus on performance. We are focused on the architecture-independent portions of this code at the moment. That's the vast majority of the implementation, and the vast majority of the concurrency portions of it are embedded in that. We've been taking what we call a spike-driven approach, which I'll tell you about now. So one of the features of Nova is fair semaphores. This is their informal documentation, which we've formalized. What we do is we expose the various pieces of this state as separation logic assertions. So here we've got like the counter. The value of the semaphore is exposed as sm.counter of an object and the number. And then we can expose the operations. What does it mean to sem up or sem down? Well, first it means to resolve the selector. You can think about these as like file system handles in an operating system. So you resolve the selector, you check that it is actually a semaphore object, and then you do this increment operation. Each one of these things, so we're saying that this hypercall occurs in 2 logically atomic steps. The first one is that resolution, and the second one is the increment. Each one of those steps is captured via an iris atomic update. And if people familiar with iris will know what this means. But basically, it says we can consume this resource SM counter. We can replace it with this new resource. That happens atomically. And then after you've done that, you get to continue with this continuation. That's what gives us the monadic bind. And we can do this for many things. We've done this throughout the entire API of Nova, and so we basically coded Nova in the separation logic. This is something I've gone off on. Like I really enjoy the idea of programming in separation logic and using that as the specification. Works very well, and we can do verification against it. So this is verified in Rocq. What does that mean? We've taken these logical specifications, and we've shown that the C++ code that implements them actually takes these steps at the appropriate times and maintains all the other invariants. Now I told you that, sorry, this is what it looks like, and it's a little small. Up there in the top left corner, you can see the source code. This is the actual source code of Nova. We made no changes to it at all. This is the specification of that function. This is Coq code, or Rocq code, sorry. Then you can see this do up, which you can't really read, I'm certain, is the equivalent of sm.anchor. So it's actually mentioning the specification that we're exposing there. And then this is our iris-based proof. And if you actually looked at these slides in great detail, you would see there's some things that you may not recognize, and those are the Skylabs AI automation, which is doing things like symbolic evaluation of C++ code. Now, when you verify something like a hypervisor, you have to be very careful about what you do. Like I said, this is verified, but that doesn't mean we verified absolutely every single line of every bit of code, because when you execute this thing, you're going to start by running some assembly code, which, we don't have a program logic for assembly, we have a program logic for C++. So when we talk about a spike, what it is that we've done is we've carved out kind of like the interesting control flow that happens at that level. So this is the for semaphores. And we have verified the things in green against specifications of the things in orange, right? And why is it important? Well, if you were to look at like EC unblock, if you were to verify EC unblock, you would need to go and verify the scheduler, which will start which will start executing something else, which will ultimately end up, back in the entire rest of the system. So we've taken various pieces of this and kind of put them out, and what we do is we focus on various functions, we verify them against other specs, and then we kind of push our way down, usually trying to focus on the most interesting stuff where there's concurrency and stuff like that first. This is where we are right now. So there's a lot of stuff that's green. The top level spec is green stuff. This is stuff we've actually verified software running on top of Nova against. We've done a lot of proofs there. The proof column here talks about what we've actually verified within Nova, as well as a bunch of stuff over here. The colors are not great. So this is actually green as well. And you can see that we've kind of where we've been focused on some of our work. So that's the end of the talk. I hope I'm on time. Actually, don't know. So all of Nova is open source. The source code's available here. We've got a project website that is the formal methods at BlueRock is at the second link. And the brick program logic and is open source. You can take a look at that online. That is now owned by Skylabs AI, where I work now. And the automation that we've developed that is being used in this is also a product of Skylabs. And in all of these things, we're very interested in collaborations, people interested in C++, or just real systems verification. And there's a lot of interesting problems that arise when you do real systems verification at this level. So thank you so much.
Okay, we have time for questions, so Ralph.
Hi, thanks for the update. I'm curious about this automation that you mentioned. So should I think of this as an AI invoking Iris tactics, or like what is the TCP situation for that? Like how does it interact with the rest of Iris? Could you say a bit more about that?
So the automation, this piece of automation that's used here does not leverage any AI. Skylabs AI is building AI agents that use this automation, but the use of AI doesn't impact the TCP at all. So this is reflective Coq tactics or Rocq tactics that generate proof terms.
Cool, thanks.
More questions? I guess I have one. So is the dream here to maybe integrate those AI agents to help automate these proofs using automation you have?
Absolutely, yeah. Yeah, and we've seen some kind of interesting results on this. Like if you think about many of the things that you do in verification are relatively easy. And then you have that one loop that you have to write a loop invariant for or things like that. We found that actually AI agents are pretty good at some of these things. And you think about this in like the context of like abstract interpretation. We have very good theory around much of it. And then there's this kind of questionable part about like widening and narrowing and stuff like that. And I think this is a place where agents can use a lot of data to give good answers there very heuristically and not enlarge the TCP in any way.
Very good.
All right.
Any more questions?
All right. Thank you.
Let's thank the speaker again.